Lesson 12.4 is on finding the sum of an infinite geometric series. So an infinite series is where the series will continue forever. If I were to just list off, I don't know, let's say the ratio is 2. So each of these get multiplied by 2. And this dot 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 makes it infinite. So the question is, can an infinite geometric series have a sum? Well, if we were to add all of these numbers together, our sum is just going to keep getting bigger and bigger and bigger. And so we can't really get to one number for the total, for the sum, because, you know, these numbers just keep getting bigger and bigger and bigger, and that sum will just get bigger and bigger and bigger. So what if we were to, so on that one, the ratio was 2. Let's say we were to take an example where the ratio was, let's say, 1/2 instead. So if I just flip this around, let's say I start with a 16. Multiply by a half, I'll get 8, and then 4, and then 2, and then 1, and then a half, and then a fourth. And so let me kind of show you what happens with this. We have this red ball right here. And let's just say that this is, I don't know, the wall, that black line over there. So if I want to look at thinking about this in terms of distance, I want the total distance to the wall if the ball only moves half the distance each time. So here's that first distance. That could be the distance of 16. Well, now it's going to go halfway. Let's say it goes to here. And so now the distance from there to there is 8. So we would be adding those together. Then it's going to go half the distance again. And this distance will be 4. And we'd be adding these together to get the sum. Now I'm going to go half the distance again. And what are we at? 2. And then we go half the distance again. And we're at a 1. And so, you know, I'm kind of using a real example here where I'm going to hit the wall, you know, physically, but mathematically, can you always go half the distance to something? And mathematically, this ball keep getting half the distance, or keep moving half the distance to the wall, and never ever touch it. It's just going to keep getting closer and closer and closer, but it'll never touch it. So what's going to happen is these numbers keep getting smaller and smaller and smaller, and when you add all these together to find the sum, eventually you're adding really small numbers over here. It's almost like you're adding 0 because the numbers are so small. And so there are some infinite geometric series where you can find a sum, and that's going to happen if your ratio is less than 1. So here's something just to put in your notes, and we kind of talked about in the last slide. If the absolute value is thrown around the ratio just so that we can stay between 0 and 1. If the absolute value of your ratio is less than 1, then there will be a sum, and why is that? That's because you keep adding smaller and smaller numbers. If your ratio is greater than 1, there is not a sum. So sometimes your answer will be no sum. And then why will there not be a sum? That's because you keep adding numbers that are getting bigger and bigger and bigger, so your sum keeps getting bigger and bigger along with it. So when we see problems like this, is there a sum or not a sum? Really, all you're doing is you want to take a look at what your ratio is. Well, first, you may want to notice that this is what an infinite geometric series will look like. You'll see it's going to infinity. You'll also see that you have what looks just like a geometric rule right here. You have A1, you have your ratio raised to the n minus 1 power. So this ratio is a negative 1/4. If we take the absolute value of it, it's just 1/4, which is less than 1. So this one does have a sum. We could find it. This ratio is 2, which is greater than 1, which means there will be no sum. So you got to pay attention to whether or not you can find the sum to know if we move on to using the sum formula, which is on the next slide. So when a sum does exist, we have this nice formula. It's my favorite sum formula just because it's the quickest one to use. All you need to know is your first term and your common ratio. But because all of you know, that last one we saw, I don't know, was it 1 to infinity? This sum formula right here has an A1 and it has a ratio, so I could certainly plug it into this formula right here. I would lose all the credit completely on this problem though, because the ratio is 2, it's greater than 1, which means that no sum exists. So you have to be really careful, because you really could use the formula on any infinite geometric series problem, but half the time a sum will not exist, and you really have to pay attention to your ratio. So here are what those problems look like. And again, you just identify your A1 and your R, plug it into the example. There's a video on it, so I'll skip going through it in this intro video, but that's what it will look like. And there's a video on these problems too. If you're given the sum and the first term, how can you find the common ratio? So the video will walk you through how to plug it into the formula and find R. So watch that video. And then lastly, there are 2 concept videos on applications of infinite geometric series. So this ball, I won't do the problem, but I'll just talk about what's happening. You know, it drops this distance, but it's going to bounce up 75% of the previous height. So it's going to go up to about there, but then it bounces down again. And then when it comes back up, about 75%. And so this is because mathematically this ball would bounce forever. We know that gravity plays a hand, but because it's always 75% of the previous height, that makes it an infinite geometric series, because you can always go 75% of the term before you. And here's the last slide. Again, there's a video for this problem as well. It's another one of those application problems where a pendulum is swinging. Let's just pretend it starts out here, and it's going to swing one full swing, and then, so that's the 24 inches, but then it just goes 2/3 of the swing before it. So it'll swing back just 2/3 to there, and then it'll swing 2/3 of that, and then 2/3 of that, and then 2/3 of that. Eventually we know gravity would keep this from swinging or from moving any further, but because mathematically you can always go 2/3 of the previous distance, that makes it an infinite geometric series, and you will be able to find a sum. So watch the video on this just to see how these get set up. And there's your intro video. Hopefully it was shorter and sweeter, but make sure you watch the other videos. Don't skip out on that, because if you skip watching the videos, then you definitely are missing the big picture on what we're trying to do here.